Good morning, everyone. Welcome to the One Concept Per Day portal. And this question is the second question. In the previous question, we had seen about how to apply FBDs and making use of the FBDs. How do you arrive at the torque equations? And making use of torque equations, how do you find out the values of normal reactions? We have seen until so much. Okay, and this was purely related to the HL portion. Now, this particular question is related to HL and SL because it's taken directly from the mechanics part. Okay. So the diagram represents a balloon just before takeoff. The balloon's basket is attached to the ground by fixing two ropes. Okay, so there's a balloon over here. There are two fixed ropes over here, which has been attached to the ground. This makes an angle of 50 degrees each. Okay, there's a force F vertically upwards, 2.15 into 10 cube Newton acting on the balloon. So vertically upwards. So what I will do is I'll write this is my balloon and I'll write it like this over here. This is your 2.15 into 10 cube Newton is been acting upwards. Then the total mass of the balloon and its basket is seen to be 1.95 into 10 square kg per 10 square kg. So 1.95 downwards. The total what is this actually? Total mass of the balloon and its basket is seen to be so much. Look into it that this is mass. Okay, but what do I need? See here, this is force. And here it is mass. So what I should do? I should multiply this by 10 to give rise to 1.95 into 10 to the power of 3 Newton. Okay, this is what I should get, right? So this will be the force now. Now I can write it happily here. Because whenever you are writing anything, it should be only one type of unit. So you cannot represent mass downwards over here, force upwards over there, right? So that is a rule in FBD. So see to it that if you are mentioning acceleration here, this should also be acceleration. If you are mentioning force here, this should also be force. Because we are drawing by vectors. Vectors should always represent only one type of quantity. Okay. Now let us see. State the magnitude of the resultant force on the balloon when it is attached to the ground. Okay. So what is the resultant force acting on the balloon when it is attached to the ground? Now what is your answer? Most of you will think that I should subtract these two and get the answer, which is incorrect. The reason is because, read the question once again. It says resultant force acting on the balloon when it is attached to the ground. When it is attached to the ground, what happens? It is not moving anywhere. If it is not moving anywhere, what is the total force? Total force is 0, right? It will not be a subtraction of anything. If it is moving, see, if you say this has some positive value, according to this value, see, this is a 2150 here and 1950 over here, and I say I will subtract one from the other, then there is a net force acting, and this net force will make the balloon to go upwards. Is it going? It is not going because it has been tied with this strings, rope, and as a result of it has been held there itself. So therefore, definitely, since it is not moving over here, the net force is 0. Okay, there is one thing which is very important to understand. See, always read the question properly. Do not jump to conclusions immediately. Right, next. Calculate the tension in either of the fixed ropes. You need to find out what is the tension acting on it. What is the tension acting here? What is the tension acting here? How do I find? Now you see, the net force here is not 0, it is something else. Then where is that extra force coming from? The extra force is coming because there are strings which have been attached, which I have not considered over here. So therefore, let me consider this is tension T, this is tension T here. Okay, and since this angle is 50, this angle is 50, this angle should be 40 degrees because 50 plus 40 would be 90. If I drop a perpendicular here, this would be 90. Total angles in a triangle will be 180. Okay, so therefore this should be 40. If this is 40, this is tension T, the component of this tension will act downwards. What is that value? It should be T cos 40. So due to one string, but this is when attached by two strings, right? So this should be once again T cos 40 due to the next string. Right? So therefore, the total force that is acting due to the tension alone is seen to be 2T cos 40. Now, as a result of this, this force plus this force is not making it to go upwards. Right? Though there is an upward force which is very higher, but these two forces are always trying to pull it downwards so that the resultant force is 0. So what you should do? You should just equate them and then solve it. Right? So what I will do is I will just write this as 2T cos 40 plus 2T cos 40 plus, what is this force here? 1.95 into 10 cube. I will expand this. I will write this as a 1950. 1950 should now be, these are the downward force. Sum of the downward force is equal to sum of the upward force. What is the upward force? 2150. I multiply it by 1000, I get 2150 here. So I'll write this as 2150. So therefore this will be 2t cos 40 is equal to 2150 minus 1950. How much is it? This will be, here you have 50 and here 150. This should be around 200 Newton, right? So therefore 2t, or maybe I can write t is equal to 200 divided by 2 cos 40. Now let us calculate what is this. 2 ones are 2 hundreds are. It should be 100 divided by cos 40. Anyway, still I need to find out this value. Let us find out what is that value here. So this should now be equal to, so this should be cos 40. 40, I take 40. Cos 40, what's the value? Cos 40, I get 0.776. And then I take the reciprocal of this. I take the reciprocal. 1 by cos 40 is 1.3. Multiplied by 100 would be 1305. 130.5. This should be 130.5. Now you see, what is this now? This is given in terms of 3 significant figures. So I need only 3 significant figures. So this should be equal to 131. What is the unit? Newton. Newton. So 131 Newton should be your answer. Okay. Let us move on to the next one. So continue. Okay, this is a continuation. Of course. Then this question is taken from November 2005. Okay. Then the fixed ropes are released and the balloon accelerates upwards. Now what do? You cut the ropes, right? And as a result of it, it moves upwards. Calculate the magnitude of the initial acceleration. Now what's happening? The moment you release it over here, and the moment you cut it here, then what happens? There's no tension in the rope, right? There's no tension in the rope, and the only force that acts here are nothing but this force and this force. Now let us draw the free body diagram once again. So what does the free body diagram tells you? You have 2150 acting upwards and 1950 acting downwards. So net force is acting upwards, which is equal to how much? Net force F net would be is equal to 200 Newton acting upwards. Now I want to find acceleration. Acceleration A should be 200 divided by mass M. What is the mass of the balloon? It should be have been given somewhere over here. The total mass of the balloon and the basket is 1950, right? Sorry, 195 kgs, not 1950. It's 195 kgs. Okay, see, I did not take 1950 because that's a force over here. Just take the mass over here, which is 1.95 into 10 square, which is 195 kg. I'll write this as equal to 200 divided by 195, which will now be equal to 200 divided by 195, which would be 1.025 or 1.03. 1.03 meter per second square. 1.03 meter per second square. Okay, then next. The balloon reaches a terminal speed of 10 seconds after takeoff. Okay, reaches a terminal speed. The upward force F remains a constant. Describe how the fraction of magnitude of air friction on the balloon varies in the first 10 seconds of its flight. So what does it say? The balloon reaches a terminal speed 10 seconds after takeoff. Initially, it is the same. Okay, so F resultant was seen to be 200 Newton, right? Okay, and then the value of A was being found out. Now what does it ask? The upward force F remains a constant. Upward force F remains a constant. Describe how the magnitude of air friction on the balloon varies during the first 10 seconds of its flight. So how do you do this? You can say that air friction increases with velocity. Because it's for 2 marks, you can say, okay, air friction increases with the velocity. Why should it increase with velocity, or why do you conclude it like this over here? Because he says the upward force F remains constant. See, when there is an upward force acting on an object, the object will continue to accelerate. Okay, which means what? It should definitely keep on accelerating. Its velocity should keep on increasing. But what does he say? He says after 10 seconds after takeoff, you observe that the balloon reaches a terminal velocity. Which means though there is a velocity increasing, let us say velocity at 10 seconds is equal to some 7 meter per second. Okay, 7 meter per second. Then 11th second, let us say it should be 8 meter per second. But in that case, here it should be, velocity should become higher. But what's happening over here? It's not higher. It says it's only again 7 meter per second. Why does it happen? Because there's a opposite force over here which is trying to increase along with the increase in velocity. So therefore you can say air friction increases with the velocity. You can say that. So then you need to find out, so what happens to describe how the magnitude of the air friction on the balloon varies during the first 10 seconds of its flight. How does it vary? Okay. So initially, when you have the threads which is being connected to the balloon like this, okay, you left it over, you cut it over here. At what time did you get at t equal to 0 seconds? Okay, at t equal to 0 seconds, what was the velocity of the balloon when it just took off? It was 0 meter per second. But as it started going from 0 to 10 seconds, what happens to the velocity? Velocity also went from 0 meters per second to a terminal velocity, right? So therefore, okay, you can say the velocity also increased from 0 meter per second to terminal velocity, okay, linearly. Now, so therefore, now why linearly? If you ask this question, what was the acceleration here? We found out the acceleration somewhere here. How much? 1.03 was the acceleration. 1.03. So therefore, v equal to u plus a. This should be equal to 1.0 times 1.03 times 10 over here, which is equal to 10.3 meter per second, right? So therefore, you see, some 0 meter per second to 10.3 meter per second, the velocity kept on increasing. So with this, we come to an end to this particular question. So if you like this video, do like, share, and subscribe to my content so to get more updates. Thank you.